Richard.
Right, okay. Hello, my name is Richard East. I'm chairing this institution virtual presentation tonight. I'm a past Railway Division Chairman from 2016-2017 and also a trustee of the IMechE. And I'm very pleased to introduce this meeting tonight, which has a dual purpose. One is allowing Felix Schmid to talk about his Railway Division Chairman's address, but also it links into Sir Seymour Biscoe, who is one of the prestige lectures that the institution presents. Seymour Biscoe, let me just have a look. Well, just waiting for the email to start up. Seymour Biscoe is a gentleman that Felix will be talking about in his presentation, and he was born in the 19th century and was certainly involved a lot with the Institution of Mechanical Engineers, Institution of Civil Engineers, and other institutions, and was heavily involved with the situation and developing railways in the Indian subcontinent. He was also involved with the Railway Industry Association, which is where all our links come from now. I'd also like to encourage people to look at Railway Division events which are available for people to download from a virtual perspective, and these can be accessed from the Institute of Mechanical Engineers website. If you look on the events, make sure you can click on the all events rather than just the paid for events, and if you filter them for Railway Division, you can see all the other events that are available for people to log into and access. And as an example, there are other presentations from the centres tomorrow night, Wednesday night and Thursday night, so there's lots of information available. Also, from a Railway Division perspective, we are reformatting the annual lunch that we hold at the beginning of each year, and Felix will cover any questions about that later. If you have any questions during the presentation, there is a format, there is a means to type it in, and it would help us if you could put information about yourself within the text box so that we can understand a bit more about the information that's available. I'd now like to take the opportunity to introduce Felix. Felix is the Railway Division Chair for 2019-2020, sorry, from 2020 to 2021, and has been in the UK for 40 years. So, and he's going to talk a lot about himself and talk about the challenges of systems engineering. So, Felix, over to you.
Thank you very much, Richard. In the time while Richard was giving the introduction, you will have probably looked at the slide about Sir Seymour Biscoe. The most remarkable, to my mind, the most remarkable thing was that I thought, oh God, this poor guy had only a 1-year retirement, because he retired in spring 1937 and he died in autumn 1937. Well, I discovered later on, of course, that he was 77 by that stage. So it's definitely somebody I want to emulate in terms of doing things into old age. Anyway, I'm now going to talk to you as a little video clip so you can actually see my face. And that's
Welcome to the Seymour Biscoe Tritton lecture of the Institution of Mechanical Engineers for 2020. My name is Felix Schmid and I'm the chairman of the Railway Division for 2020-2021. This is also my Railway Division Chair's address for this year, and I'm going to introduce you to systems engineering for railways. I'm going to talk a little bit about the historic background to this topic, and I'm also going to talk a little bit about myself.
Okay, as you can see from this slide, I'm interested in systems thinking, in railway traction systems and railway control. I'm also very interested in ergonomics and people in systems, and that will hopefully become clear during my talk. I will cover a little bit about railways as complicated and complex systems and what the consequences are of this. And I will talk about the systems approach to railways. because the railway is probably one of the most important systems of systems we know. And my objectives are to make you think about change, to make you think that change is important and will always have to happen. I'm going to talk to you a little bit about the value of people, and throughout you'll probably see that education is probably quite worthwhile. So I'm not going to go into detail here, but I'm going to apologize first of all that this is an educational talk. It's not just an entertainment talk. I hope there are some small entertaining bits in it, but I'm also going to cover a bit of railway history, and particularly something relevant to London, because notionally this event is taking place in London. And so I'm going to talk about complication and complexity and the sort of things which come out of that. I'm going to talk about the V system life cycle, because that's what I've been teaching our students for the last 25 years or so. So, what is a system? Well, it's basically a thing which exists in an environment. And the important thing is that it is influenced by the environment, it influences the environment, and it has either a single purpose, but in many cases it has multiple purposes. There's another definition which basically talks about the elements of that system, that it's got to be a unified whole, that it's described by spatial and temporal boundaries, and as I said, it's very strongly linked to its environment. It can also be a set of principles or procedures according to which something is done, an organized scheme or a method. And I think you're probably quite happy for me to call the railway a system, because it has a very clear purpose. It's made of lots of different bits. Now, over the past few years, people have started to talk a lot about systems of systems. And many people sort of tend to think it's only something which has happened in the 20th century, 21st century. Somebody has got their microphone on. Could they please switch it off? So a system of systems is a large-scale set of integrated entities. They are different from each other. Each of them could work on its own, but as a whole, they're actually producing a common goal through what are called emergent properties. So the property of a railway only comes about when you actually put the track, the trains, the signalling, the stations, etc. together. Each on their own can work, but it's not much use. So some people tend to think that nature is an example of a perfect system of systems. And that is to some extent true, but if you look at this tree, it obviously did something wrong. The seed for the tree landed on a rock, and for many years that was a very successful place to grow, and it grew to quite a good height. But then there was a strong storm and the tree just fell over, and that was the end of that tree. Now, here is another tree which also made a mistake. In this particular case, the tree actually grew into a crack in a rock, and as it grew and grew, eventually it split the rock and committed suicide. So once a tree has actually chosen where it's going to be, it has no longer an option. It is going to be there until the end of its existence, or until somebody cuts it down. So nature is a system of systems, but it's far from being perfect. Now, there is a system of systems which I'm very interested in, of course, which I've just talked about, which is the railway. And the railway is, to some extent, a typical generic system of systems, because it's got, each element has got managerial, developmental and operational independence. The requirements for the system evolve very quickly. There's lots of stakeholders who want different things from the system, whether it's employment or transport, etc. There is emergence, which results from the inter- and intra-systems interactions. And systems of systems are often geographically dispersed. And of course, all these things relate to the railways. So there were 150 railways originally in Britain, with separate owners, with rapid growth of networks, of services, of the passenger numbers, the numbers were huge. All the stakeholders, whether they were passengers, governments, suppliers, they all had very different needs and aspirations. And as people started to travel across the boundaries of these small operations, the whole network needed new rules and new facilities. And eventually, the system of systems spread across the whole country. It was connected effectively to the physical parts of the system. I'm sorry, there is quite a lot of noise, and it's coming from somewhere else. I don't think it's coming from me, so I apologize for that. But anyway, as this all came together in 1948, British Railways was created, and it tried to integrate it all. And of course, we know that in the 1990s, a process started which turned the railway back into something which was much more similar to its original nature. But of course, it was also a very successful approach to some extent. So I'm now going to talk a little bit about history because I promised I would do that. And 216 years of innovation started really in Germany, in the mines of Eastern Germany, where the miners decided to put down planks with a slot in the middle, and they had something called Huns, and these Huns could be pushed along those tracks, and they had the two functions of guidance and of smooth running. And that is still probably the key characteristics of a railway. It's a very useful thing to think about, that in the 1600s, the Germans had already invented effectively the railway. And the idea was, of course, that a grown-up or a child could push far more load when it was smooth running and it was guided, and the tunnels could be much narrower than they would have to be otherwise. And this form of transport was introduced into the Lake District in Britain in, again, 1600 approximately, because they were seen as the expert in the technology. And since then, there have been more and more railways of different types. So here we have got the earliest railways of the 1700s. They were quite rustic tracks. They were very often referred to as railways, railroads, tramroads, or tramways. They were not referred to as railways. Now, actually, the word tramroad or tramway is very interesting because it comes from the German word trammel, a piece of wood, or a log. And so these were actually log railways. And so the Germans have had a very strong influence on the development of the railway in the UK, and also its name for the tramway, certainly. Now, one of the big things which railways do is they transfer the load from the wheel to the ground. And that's probably one of the most significant innovations which came about from about 1700 onwards. Because the wheel rests on the rail, the maximum dynamic wheel force is 350 kilos, which is effectively 35,000 bags of sugar, 1 kilo bags of sugar, and that's resting on just one wheel on a rail on a surface which is about the size of a thumbnail of a not very large person. And so that creates, of course, a huge pressure. And what I'm showing here is the pressure distribution, starting with the wheel on the rail right at the top, and then going down to the interface between the bottom of the sand blanket and the natural ground. And so that goes in a logarithmic scale, which is very important. It goes from 2.8 kilonewtons per square millimeter, so that's 280 bags of sugar on a square millimeter. That's a hell of a lot. And the railway survives that year in, year out. Down to the bottom of the sand blanket, where we have got about a third of a bar of chocolate sitting on a square millimeter. And that's why the railway can go across very different routes, etc. Now, of course, once you had the track, people had to start thinking about what to put on it. And quite a lot of the early railway engineers didn't believe that a smooth wheel on a smooth rail would actually work. Trevithick, Burton, Blenkinsop, even Eisenbach, and Brunel were convinced that steel wheels on steel rails would inevitably end up rotating and not doing anything. And that was even the case for Richard Trevithick, who was really the first person who created a working steam locomotive. He built it for Coalbrookdale, at the Coalbrookdale foundry. It had a little drawback in the sense that there was only one cylinder and one piston, so if you didn't get it started, then it didn't work all that well. So that was in 1804. The next locomotive was built in 1806, and the biggest discovery Trevithick made was that if you let the steam from the exhaust into the chimney effectively, it creates a vacuum and it produces much greater heat in the firebox and therefore in the boiler. And Trevithick had a new locomotive built, which was called Catch Me Who Can, and he demonstrated that in Bloomsbury, so very close to where Euston Square LUL station is today. He charged an entrance fee, but unfortunately the wheels broke the rails. And I'm saying that very specifically because Trevithick had actually serrated the wheels and in order to improve adhesion. And unfortunately, those serrations actually broke the very weak cast iron rails which were available, and he gave up railways because he had no money left, and he went to America and turned to some other ventures. So not a big success, and really it was John Blenkinsop in 1811 who came up with a solution which worked quite well. He placed a rack next to the rail, and that rack was engaged with by a toothed wheel, a pinion. The pinion was driven from the two-cylinder engine in this particular case, and it therefore propelled the train. The rail wheels were just running freely. They didn't do anything. Now, you might think that was not a very good idea, but the system worked for about 25 years between 1812 and 1835. It was very successful. And later on, of course, Marsh, Rickenbach, Abt, Locher, Strube, and others adopted rack and pinion systems for railways which could climb much greater and steeper hills. Now, Mr. Burton was somewhat bizarre. He invented the steam horse or propeller in 1813. Now, you might think it's a very peculiar thing to have a walking railway engine, but it was actually quite successful, but only for 2 years. They managed to get up gradients of 3% at Crouch, and that was enormous for the time. And as I said, it worked quite well, but it blew up because somebody had tied down the safety valve. Not a good idea on a steam locomotive. In 1812, so just after Blenkinsop had started his railway, Christopher Blackett, who owned Wylam Colliery, asked his colliery supervisor, William Headley, to do an experiment on adhesion. And what you can see here is the experimental vehicle which he built. It was a four-wheeled vehicle which had weights on it, and then 4 men who cranked the vehicle forward. What he wanted to demonstrate was that with the adhesive load of the locomotive, one could actually pull more than just the locomotive. And it was very clearly demonstrated, and to my mind, William Headley is probably really the inventor of railway locomotion using adhesion steel on steel. And you can see that's quite a successful principle. Adhesion works, and an old Lisbon tram can probably do about 12%. Some Lisbon trams manage 13.5% on adhesion, but that's a bit dodgy because it's basically by jamming themselves into curves. Now, George and Robert Stevenson took together Trevithick's work and Headley's work, and they built the Rocket. Well, Rocket was number 19 of their production, and for the competition for the Liverpool and Manchester Railway at Rainhill in October 1829. And people tend to think about it as a speed-based event. because the locomotive could reach 30 miles per hour safely and sensibly. But it was also very much about reliability, because the directors of the company wanted the trains to travel frequently between Liverpool and Manchester in pretty much a bit more than an hour and a half. So the rocket proved to be very reliable, and it was the only locomotive who finished the trials. But I do want to reinforce William Hedley and Richard Trevithick actually developed the principles, and Stephenson's applied it. Now, because we're in London, I've got to throw Mark and Eisenbach-Brunel Kingdom and Eisenbach-Kingdom-Brunel into the plot. Mark lived from 1769 to 1849, and Eisenbach from 1806 to just shortly after 1850. I don't know where those numbers have gone. And this is a little bit tale of invention, ambition, and engineering and greatness in London. And you will see why it's important a little bit later. Mark Brunel, one of the first ventures he did after making pulleys in Portsmouth, he built a huge sawmill for the Chatham dockyard. This is a very amazing piece of thinking, because the wood would arrive into a basin from the River Thames. It would be floated into a canal. It therefore wasn't damaged by being knocked or trailed along the ground. It was then lifted up into the sawmill. That building still stands, and some of the sawing machinery is still there from 1814. Once the wood had been cut, the cut baulks were put onto a train, which was also steam operated, and you could see the overhead railway where it was then put to the storing and survey area before it was built into ships. Now, the interesting thing is that this was actually a very broad gauge railway. I did know the number of the width at one point, but I can't remember. So if anybody in the audience can let me know, that would be fantastic. It was something of the order of 9 or 12 foot. And that's, of course, very relevant later on. Mark Brunel also built a sawmill for veneer. Now, veneer is a very delicate thing to do, and it was an amazing piece of engineering up the Thames at Battersea, so quite a long way up the river. And this is an illustration of his sawmill. And oops, that didn't arrive. So let's go back. So the mill could produce veneers and thin boards using 18-foot diameter saws, which only Brunel could actually make work. The mill burnt down, but it had been rebuilt by 1816. So a very successful venture, but eventually it was not a big success because Brunel's partner left him. The next thing which Mark Brunel did, and we are still benefiting from that, was to build the tunnel underneath the Thames between 1825 and 1843. Project which took rather longer than planned. It was supposed to be about 3 or 4 years, but there were quite a lot of problems. The important thing for me is that Brunel actually invented the shield method of tunneling, and on the left-hand side you can see a shield with people working individually at their own pace. So it was very important to mark that people didn't work by the amount of material they got out. They had to work safely, and they had to be paid a daily wage rather than by how much they got out. So he was a very, very socially minded and intelligent man, because he expected that people paid by piecework would rush and would therefore put the project at risk. So this is a picture of the plan view of the tunnel. There are 2 small holes at each end of the tunnel, which were for the pedestrians, and the original concept was to actually have ramps going down for carriages which could go underneath the Thames. It was a fabulous idea, but the money ran out again just at the point when they were going to start digging those deep shafts for the carriages. Now, this, of course, is still with us, and it's now part of the East London line of London Overground. It's a fantastic monument. Unfortunately, you can't go walk through it. It would be really very nice. So, Mark Brunel, while he was working on the Rotherhithe tunnel site, also did some very interesting experiments for building bridges without centering. So what you can see here is an experimental design of an arch which was 60-foot open span hanging out in midair, and you think, how's that possible? Well, it was possible by having lots and lots of different materials building the bridge as if it was reinforced concrete out of bricks. So a fantastic design, and again, a testimony to Mark Brunel's genius as an engineer. Now, his son, Eisenbach Kingdom Brunel, decided to build railways, of course, and I still think it was influenced by his dad's railway at Chatham Dockyard. Eisenbach built a railway with broad gauge because he felt he could run smoother and faster, and he did achieve that. And what we see on the right-hand side is the Great Western Railway through Sydney Gardens in Bath, still a very attractive area for the Great Western Railway. Now, I'm going to talk a little bit about John Cookbourne because I like him very much. He was an artist who basically painted railways and then produced books with lithography or etching, which were sold to the public, and it was a great success. So on the left-hand side is his take on surveying railways, and on the right-hand side is a very detailed and accurate representation of Swindon Works. Now, in most paintings of Cookbourne, people exist, people are very important, but people are smaller than the machines because he wants to really highlight the grandiose nature of railways of his time. This is another of his pictures. This is the Warncliffe Viaduct, which is on the early part of the railway to Bristol. Beautiful construction, and of course it's still here, and it will long survive the Heathrow Express trains, which are basically going to the scrap heap. So a fantastic monument to engineering, to Eisenbach Kingdom Brunel, and just a wonderful story to me. Now, those experiments at Rotherhithe, of course, led somewhere. Eisenbach was never shy of using his father's work. So in this particular case here, he built the Maidenhead Bridge for the Great Western Railway, which is a beautiful bridge, very, very slim. And people were amazed and said, this drawing will never work, the bridge will collapse. You can't build this without a wooden framework underneath, which is then taken away at the end. So the bridge carried two 7-foot gauge broad gauge tracks. It was built entirely of brick, and the interesting bit is that it was 60 foot wide, 120 foot wide, so double the experimental size at Rotherhithe, and it rose very, very little. The directors of the company refused Brunel to build the bridge without a framework, and so he built it with a framework, but the bridge was actually 3 inches away from the framework. And when the bridge was finished, they just made it collapse, and everybody was absolutely amazed that it had worked. So back to systems engineering and railways, but I hope you enjoyed the historic element just now. So for me, railways are both complicated and complex, and I've come up with this sort of butterfly of railway complexity, with lots of people have helped me develop. And effectively, you have got 4 or 5 main factors which make the railway difficult to manage. There's what's called complicated elements. And if you go from the left, you have got organizational and physical dispersion, which of course is essential for a railway because otherwise it can't reach its customers. And it's both organizationally dispersed and physically. You've got the organizational side, you've got supervision, which is difficult. You've got job functions, which are all along the railway. You've got asset information, which is distributed. Physically, the assets, of course, are distributed, the customers are distributed, and the staff is. The sort of pinkish branch is about the diversity, the heterogeneous nature of the railway. You've got lots of different components, component types, material types, asset performance. And on the organizational side, you've got different staff skills, you've got mixed traffic operations, you've got the stakeholder requirements, etc., the funding models. So this makes the railway difficult to manage, but not impossible. Then we've got other elements, which are what I call the complex elements. And on the left-hand side, the blue is variability. So you've got physical variability, like the ground movement, ground stability, weather, adhesion, etc. And you've got the organizational variability. Staff don't perform as well during night as they do during the day. Staff do perform less well when they don't have the right incentives. You've got third-party activities, which are very difficult to manage. And of course, you've got the economic context, which we are suffering from at the moment. On the right-hand side, the combination of those two branches make up what's called the interdependence. It's the relationship between the subsystems. If we take the wheel and the rail, they are very, very tightly linked. It's called coupling, and physical coupling between those has to be absolutely perfect. You've then got the organizational elements of coupling, which is timetables, rosters and schedules. If your trains are not available, you can't run a service. If you don't follow the regulations, things don't work. And then you've got the interactions, which is a similar element to coupling, but it's the forces which exist between the different elements. It's also about the products and processes, etc. So technical systems are defined and designed by people, but those factors of complexity and complication will always come in the way. So Crossrail has a long history with a large number of stakeholders. It was an ambitious, or still is an ambitious, project, and to some extent the plans are somewhat disjointed. And just showing one example here, which is the signaling system. On the east side, we've got legacy AWS and TPWS in order to control the trains. On the west side, we have a legacy automatic warning system and train protection and warning system as well. Slightly different installation methods. Then we've got, for the link to Heathrow, we've got ETCS level 2. So that's the most modern system. And through the center, we've got a classical metro CBTC system. Now that's fine. It's a complicated system because there's lots and lots of components, lots and lots of connections, but it's also complex because it works with people, and at the transitions between the systems, both people come involved and the technological inadequacies are exposed. And so when we are designing systems, we need to make sure that they are as simple as possible and as complicated and complex as absolutely necessary. And this is an example of dispersion and diversity. It's from a friend of ours in Australia. And what he shows here is the types of point machines in one state of Australia. And you can see there are lots and lots of different types in varying numbers. I've counted them all. It's 2,200 point machines made of 29 different types. Now, that is not impossible to manage. You can manage it by lists, databases, procedures, and regular and reasonable maintenance. A well-trained person can handle this. It's expensive, but it works. It would be far more difficult to change them all because by the time you have changed them, the technology has moved on. Now, here's an example of variability. It's also from Australia, and it shows the influence of factors on the performance of the railway. So here we have got a blue line, which is for delivery. Delivery means, in our case, reliability, the number of trains which actually run, and the green line is punctuality. And it goes up and down around to the sort of 90%, which is not too bad. The delivery around 99, pretty brilliant. But if you then look on the right-hand side, the sort of square area, that's when the passengers disappeared because of COVID. So what we can see is that a railway without passengers works much better. Now, that's not a good lesson. What is a good lesson is to say, if we actually manage the railway in the way in which we are managing it now, we will get a much better performance in future. So maybe we have to run fewer trains, but longer trains. Maybe we have to manage platforms better, etc. But if we design the system with complexity in mind, then we will get a better solution. So, complex systems don't follow predictions. They respond, they adapt, they evolve, they specialize. And of course, this is the tree of life, which has led to the human being and lots of other things. Now, Charles Perrow came up with this theory that complicated and complex systems lead to what's called normal accidents. And for complicated systems, he had the same definition as me, but for complex systems, he defined those as where subsystems are tightly coupled, so like the wheel and the rail, with meshed interactions. So there's things in there which you don't exactly understand. And he says that accidents and incidents are not avoidable in such systems, regardless of the amount of effort which you put in, because eventually a fault, a flaw will come through all the defenses which you might possibly think of and build. And I'm going to talk about Stonehaven in a moment, but Fukushima is a key example of that. There were lots of defenses, but the tsunami broke them all down. So Perrow also said that we need to abandon overly complex technology if we want to have a success. And why did I mention Stonehaven? Well, Stonehaven happened on an infrastructure which had been designed for historic weather, even though a lot of work had been done in 2010 to improve drainage from the hillside next to the railway. The flood on the 12th of August 2020 was so strong, it basically overwhelmed the drain. It pushed the stones which were on top of the drain down into the track area, and then of course it went on the track and the train derailed. Now, every precaution had been taken to avoid this, but at some point the change in weather actually beat the preparations. So Ryan Kitchens gave a talk at the software conference saying it's not a good idea to try to prevent failures because we can't predict them. So what he said, there's three factors which make it very difficult to deal with failures by trying to prevent them. One is comprehension, because very often we can only comprehend a failure once it's occurred. It's too late. Incidents are fraught with uncertainty. So that's the example of Stonehaven. Understandability is his second factor. You manage the small stuff and it doesn't prevent the big incidents, because incidents are not made up of direct causes. We only find the causes later on, or we construct them. There was the derailment at Llangennych in Wales, where a freight train derailed because a wheel set had been braked and was overheating and effectively collapsed in the end. That wheel set was seen by a hot axle box detector, but the hot axle box detector ignored it because it wasn't the axle box which was glowing. So the last one element is predictability. Learning from the last incident will not allow you to predict the next one, because complex systems are not deterministic. And so this is a picture of flooding, and of course you can't predict where the next flood will occur once you have dealt with the current one. Ryan also gave another sort of example of how we should think about failure. He said normal work has got performance variability, and depending on what is the situation, that performance variability may result in success or failure. Because if the performance doesn't work so well, you end up with workarounds, you end up with non-compliance to the rules, and that can often lead to... What's up? Oh dear, this has dropped. I need to go quickly through this.
Well,
okay. So he said, depending on the situation, these workarounds or non-compliance can lead to success, but the same workarounds and compliance can lead to catastrophe. And the example which he gives is that of a helicopter landing to retrieve some people who have been landed below an avalanche. The helicopter lands not because it can't, but its propeller touches the snow and everything's fine, everybody gets in and the helicopter takes off. It's against all the rules, but it's success and everybody's happy. Now, had the propeller hit some ice or a rock, the helicopter would have been blown up and the whole situation would have been a failure, and everybody would have said, oh, it was breaking the rules which caused it. So Kitchens suggests some other approaches because he doesn't like Toyota's 5 whys approach. He says, let's ask for how, not why. Because if you ask somebody why did this happen, they will come up with a theory, they will come up with some logic which may actually not be true. What he suggests is that you ask how, and then you get stories. And from the story, you can probably find out what to do differently next time. And you can ask the same story when things go well, because that will tell you what you need to continue to do to make things go well. And that's my example of the variability of performance is actually that sort of thing. Let's ask why things are going well on the Deansgate corridor in Manchester now and in Australia, and we can learn a lot from that. So we need to think of ways in which we can build systems which take all this into account, and we teach our students the system life cycle from CEng. And that life cycle has got a number of elements. You come up with the concept at first, you define that concept, you define the system, and during that process of time, you basically understand the problem absolutely fully, and you come up with something which can be built. And in many ways, that's where you need to think about complication of the system. You then put everything together. That's part of the validation process. You check that you have actually been able to do what you want to do. And that's the second phase, the implementation. In the third phase, you need to maintain the operation over time. And of course, that's also something where a lot of people are involved. So we can suspect that there's probably quite a lot of complexity in this area. So if we look at that in a bit more detail, then We are addressing complication on the left-hand side of the V. We address complexity at the beginning, because I said we need to make sure that systems are simple enough and just about complicated and complex enough to work. And of course, we need to make sure that people can actually operate the systems. Alex McGrath, a friend of mine in Australia, discovered this idea of the complex systems adaptive cycle. And that cycle starts with the conception, just like the V process. And you have got lots of ideas, you experiment, you do lots of things. It is reasonably successful, so you build lots of it. You invest money, like we invested money in the railways. And as we build more and more, we need to start thinking of how we make sure that it all works reasonably well. During that phase, we do a lot of complicated problem solving, and hopefully we'll get it more or less okay. We now keep those problems sorted out by having standards, by keeping good procedures and processes. At some point, something will happen, and suddenly the system won't work so well anymore. That's what we call the system release. And we need to have very swift intervention so that we don't get a completely destructive event. And we need to start thinking about what do we do next time to prevent this from happening. And so you have more innovation, more experimentation, and you stabilize again. But lots of things happen. You get non-compliance, more and more non-compliance, and that then sets up resilience failure in this area here, where the system just doesn't work properly anymore. But all this was set up much, much earlier in the complicated setup of the system. So we need to think about resilience, we need to think about possible stresses and crises, and that then allows us to improve our solutions. So we need to think very carefully about how we go through this circle so that the lessons are not lost, because we will have set up every failure very early on in the design process. A typical example of that occurred in Australia in the summer of 2020, where wear on the system had grown much more quickly than was expected. And that was basically because traffic had been increasing hugely in the past few years as the service was improved. But luckily, the railway realized what was going on and could do a lot of re-railing very quickly and in a very methodical way. So what this means, you need to observe what your system is doing. Otherwise, you end up with serious failure. So this was my introduction to systems engineering for this audience. So this was pretty much the educational part of the talk. And I want to talk a little bit about my own personal railway history. And it's really the history of myself and my brother Thomas. You can see us here at the window of a train. Our dad introduced us to railways. The family didn't have a car, so railways were the means of transport. And you can see we're enjoying it. Thomas was very keen on depicting railways, and what you can see is steam trains. You can see both freight and passenger steam trains. And inside the bowl, you can see an electric multiple unit, which of course is very typical for Switzerland. So we were both very strongly influenced by railways. We built model railways, and you can see Thomas's electrified model railway. It was a little bit cheaper than our current electrification, but it worked. And so I went to school in Zürich in Switzerland. I did my baccalaureate with Latin and Greek, maths, English, and all sorts of other things. And at the end, I decided that I would go for engineering. This was a bit unfair because Thomas had decided long before me that he was going to study electrical engineering. And I started 2 years before him. So everybody thought he was following me. Completely wrong. I was following him. I studied electronics and electrical engineering. I understood the theory. I could work with the theory, but I didn't have any feel for it at all. I didn't really understand what it was all about. And I then did a short period of postgraduate studies. did a bit of work as a software engineer in Switzerland, which was a very novel thing at the time. We had very powerful computers with 32 kilobytes of RAM and 32 kilobytes of EEPROM. Fantastic they were. And I got fed up with it. So I went to England and I started to work with GEC Traction in Manchester. And in a period of about 3.5 years, I learned a hell of a lot about practical electricity and how it works. I then went to UMIST and to the University of Salford, doing lots of different types of engineering. So I started to become a general engineer. I went to Brunel University, and that is going to come in a moment. So just a picture from my work for GEC Traction. We were working, or I was working at Newton-le-Willows, one of the very early plants. Fantastic, interesting job, because we were basically testing a locomotive and building a locomotive which was going to go to the States. And this is the crew. They were working on a different locomotive at the time, but they're fantastic, nice people. The guy here, Paddy, was a very important person in my life, because Paddy had lost half a leg on a job in Nigeria. He didn't like the way the company had treated him, and any manager coming to site was basically shouted at, abused, and got every second word was an F word. So it was not a very nice environment. I was 28, and I was quite puzzled. So I thought, okay, I can deal with this. And overnight I practiced. And the next day, when I had to go to Newton-le-Willows, I came across Paddy, and he started his usual swearing. And so I let off a steam of abuse. It was filth, really, directed at him. And he said, "Felix, what's this? Why are you saying this?" And I said, "Well, you're treating me like dirt, so I'm behaving like dirt." And he said, "Oh," I said, "could we be friends?" And he said, "Oh, yes, that's like a very good idea." So we became friends for the rest of my work with GEC. It was wonderful. The locomotive we built is portrayed here with the team working on it. And of course, there's a picture here of the boy who was in charge. So you can understand that Paddy didn't sort of have much respect for me at the beginning. We were building the second series of ZEPEX choppers. So this was a very early type of traction system with electronics. Over the period of time I've been working in the industry, there have been about 8 different technologies, fairly fundamentally different technologies to control traction motors. Resistance control, choppers of different types, choppers powered by different types of electronics, inverters of different types. And today we are, of course, dealing with IGBT inverters, integrated gate bipolar transistors. But where are we going next? So this is roughly 5 to 6 years of technology for each of those, and then the next technology was coming along. The Rolls-Royce Trent engine has had 50 years of evolution, and you can still recognize it as what it is. So maybe that's one of the reasons why railways find it difficult to introduce new trains, new technologies. It's just too much, too rapid change. So this was the period as a traction engineer and as a researcher. And I knew all the time that I would never be a teacher. I was absolutely sure of that. Our dad had been a teacher. Mum was a very bright and competent lady, very determined on our behalf. And she managed to organize for Thomas and me to do maths teaching, private maths teaching, which was funded by the state. It was a very good earner, and I started to enjoy teaching. At Salford University, I learned about classroom control. I have to share this with you because it's the Kalashnikov approach is quite interesting. My supervisor said, you go into the first lecture and you identify the students which talk, which are disruptive, and you don't say anything. And in the second lecture, you wait until they are deeply engaged in this nefarious work, and you ask them a really stupid question. And they haven't got a clue where you are in the lecture, so they look stupid. Everybody else knows they look stupid, and therefore you have peace. It does actually work rather well, but it's cruel. At Brunel, my boss, Ray Wild, said, well, you need to teach computer integrated manufacturing. I said, what is it? And he said, I don't know, but we need to teach it. So I decided not to do this with lectures, but by creating a team-based activity for the 4th year of the course. And here you can see one of the groups which was building a manufacturing center, an automatic manufacturing center. This was done for about 8 years, and in the end I managed to do my PhD in educational development on this. Towards the end of my time with Brunel, I was offered a post in Switzerland as a railway inspector, which was a very big change, but I did it in the best part of Switzerland, in the Alps, where I could test railway level crossings in the best scenery possible. It was an interesting job, but it was not my scene. I was not a very good civil servant. However, it gave me one of the important lessons about systems engineering. This is a railway in Switzerland which goes fairly high up into the Alps. Then there's a tunnel towards the top, and it's very difficult terrain. So steep cuttings, ledges, tunnels, etc. And Switzerland had come to a deal with Italy and Germany that they would carry out-of-gauge piggyback trains through the country. And this railway was chosen as the right route, but it was impossible to actually make the whole line compatible with these big trains. So what they decided to do, we need to do this more simply. We can't do it electronically. What we do, we just use some of the railway for the large trains, and in some areas, some of the tracks will be banned. So the railway will not be completely open for piggyback trains. We'll put in a technical solution to make it safe. And so they were going to use the non-secure train describer to set the correct routes, so either on the left or right-hand track, depending on where it was available, and could you create a new signal aspect which said to drivers, if you are in charge of a big train, then you must stop. If you're in charge of an ordinary train, then you can go through. And of course, it was displayed in a fail-to-safety manner. So the principle of this was the two-channel safety principle, the driver being one channel and the route setting system with the interlocking the other one. And the theory is that if both are totally independent from each other, then you get a very high degree of safety because the mistakes don't happen at the same time. And I've given an example here of a person failure, maybe 2 mistakes per 1,000, infrastructure technology failure, maybe 1 in 100,000. Both together make it a very, very low probability of failure, so roughly 1 in 5 million journeys I calculated here. And so that was a good idea. I thought not. As the railway inspector, I was not happy with this approach because basically it tied the two elements together, because the driver only had to make a particular decision if the technical system didn't work. They only had to stop the train if they were in charge of an out-of-gauge train and it had been routed wrongly. Now I did a calculation and I'll talk about that in a moment. So this is what a typical section of the railway looked like. We've got tunnels, we've got dotted lines where the big trains are not permitted, and we've got solid lines where they are permitted. And so you've got a number of points where trains could enter a dangerous area, which are shown with the red circles here and the arrows. So at those places, the railway put violet signals. So I've shown those here as I. And those signals would tell a train driver if she or he was wrongly routed that they had to stop. Now, the calculation was interesting because of course, in most cases, the train would be routed correctly. And so when you had a driver going along the route with a conventional train, whether this is a passenger or a freight train, they would see 17 situations in 3 hours where they had to ignore the violet signal. And I calculated that it would take about 15 years before a train driver would see a violet signal where they had to stop. So I was not impressed with that solution. Here is an example picture of one of these violet signals. Why am I showing it? Well, I said you can't do this, but they appealed and eventually they were allowed to do it, so the system is in operation. Happily, it's only very rarely used in earnest, but I still think it's a very poor use of people and technology. I then became an academic at the University of Sheffield. It was serendipity who made me go there, because I was went to talk about a PhD rather than going for a job interview in Cambridge for a manufacturing job. Andrew Jablonski offered me a British Rail funded post to develop the MSc program in Railway Systems Engineering. And of course, that's now at the University of Birmingham. And we discovered that porridge could be a form of educational enhancement, because in 2010, Turkish State Railways sent 30 people on the MSc program, and we were worried. Too many people from the same background, too many novices. So we set up something called the Works with Working Weekend, and Bridget and I cooked breakfast for that. And so here is a picture of the first team who were building track on the Ecclesbourne Valley Railway. They all look very happy because it's the end of the weekend and they can go home. Below is a group, a much later group, about 2 years ago. And of course, as I said, Bridget and Felix making breakfast and a group of students eating dinner in the same context. It works extremely well because people learn to trust each other, people learn to work with each other, and people start to realize that railway work is hard. It's not just fun. This is a picture of about 3 years ago. It shows Bridget Eickhoff, who is currently watching us and helping with the questions. She's really Mrs. Stakhanov on a work site like that. She works with all hand tools, demonstrates them, and in this case, a band to tighten up bolts. And on the right-hand side, you see a student who is being instructed in the use. On the first bolt, she couldn't do it. On the last bolt, she was confident, and she really became a top student after that. So here we, of course, see a bit more of railway work. But one thing which we do, which is perhaps unusual, is we carry whole lengths of rail with 20 or more people. It's definitely a team activity. If you don't do it right, it's extremely dangerous. If you do it right, it's a very sensible exercise. We did other things as well, which had not been done before. A study tour with the students to several European countries to learn how to do the things differently. We've been on heavy haul freight. We have gone on the maglev ultra high-speed train when it still existed. We have been looking at high-speed rail and metros, suburban railways and trams, and narrow gauge and mainline railways. So here is a group on the Chemin de Fer de Provence, a very small narrow gauge railway in the south of France. On the left is Charles Watson, one of my colleagues, and on the right is my brother Thomas, who comes and helps with the study tours because he is still interested in railways, even though he's been mostly working as a software engineer. We also did something mad in Singapore when the metro discovered that it no longer was running a new metro. A 30-year-old metro is not new. And more importantly, when they discovered that all their young engineers were retiring because, well, 25, 30 plus 30 is retirement age. So what you can see here is a group of Birmingham staff with a lot of Singapore young engineers teaching them about systems thinking and systems engineering. Of course, the lessons with the of running study tours became known to the mechanical engineers, and they asked me to run some technical tours. So here is one technical tour about 5 years ago, and the person who's introduced the tour is actually the tallest person at the back, Richard East. So very good fun. Here is another one of those group pictures from the last study tour, because this year's was cancelled because of COVID. And highlighted are the people who are in the local centre, in this case in Scotland. Of course, study tours are very useful for taking pictures, in this case track breaks on the left-hand side, and on the right-hand side I'm serving as a guinea pig for a narrow platform. Platforms like these you come across on the continent of Europe quite frequently. This could almost be described as a relatively wide one. I can tell you it was not good being a guinea pig standing next to a train moving through at 50 kilometers per hour. One of my charities is the Railway Children. I really like them. It's a very good charity. And in January, I will do a sleep out for the Railway Children, and I will probably ask everybody to sponsor me. Here we are at the beginning of the first 3 Peaks by Rail, a fantastic event. If you get the chance, go on it. So I said all that already. I now want to say thank you to a lot of photographers who have provided pictures for me, all the students and teachers involved, and then a lot of people, a few people providing ideas, and the people who helped with the development of the course. I'd like to highlight Sharon, Holly, Francesca, Joy, who have been absolutely essential because they actually managed the students. We just taught them. And then Deborah Hines, who unfortunately died a week ago, who was an asset to the course while it was at the University of Sheffield. And I also want to mention Brian Redfern, because he acted as my mentor at the beginning. So, very important announcements now. Richard has already mentioned all the Railway Division lectures. Here is a seminar or conference which we are running at the University of Birmingham from the 15th of December to the 17th of December. One can still register for it. It's basically about high-speed rail and its link to education. So there will be technologies, there will be educational issues, there will be organizational issues, and hopefully it will be an interesting virtual conference. The Automated Railways webinar, which we ran together with the IRSE and the FPWI and the IET earlier this year, is still available. And if you want to join it, it's now a great bargain. All the elements are still there, apart from the live elements, and those have been recorded. So it's only £65 for roughly 20 or more hours of useful information on railway automation. Now, the most important thing of this talk is my advert for VAL. So that's the virtual annual luncheon of the Railway Division. This always happens in March, and this is the first year where we can't hold it in physical way. We only can hold it in a virtual way. We're going to try and make it as much as possible like the real thing, with networking, connecting, sponsorship, with advertising opportunities. Hopefully you will bring your own food, and we will provide menus when you actually join the event. So a table costs £150 rather than £2,000, and for individuals it's £18. So it's probably going to be a very good event. This is Bridget and I preparing for the vegan menu because we thought we had to test it. Looks quite nice to me. And we also tested a meat eating type menu. So again, it worked, and all that information will be provided to people who want to eat in style at home or in a boardroom or wherever. So, thank you very much. I think it's time for questions, etc.
Thank you very much, Felix. I'd like to hand over to Noel Travers to initiate the discussion. Noel is one of the Vice Chair of the Railway Division. I'm sure we'll have some interesting questions for Felix.
Thanks, Richard, and thanks, Felix. It was interesting listening to your presentation, your lecture. It certainly took me back 25 years to the first intake of the MSc Rail Systems Engineering course in Sheffield. Mostly fond memories. I don't recall you trying your Kalashnikov trick on me, but maybe you did. So on to the question. You said at the very start, a system is influenced by its environment. Looking at the current environment, do you expect demand for rail travel to recover once the pandemic has been brought under control? And how do we apply systems thinking to influence this?
I think unlike many other people, I'm not pessimistic, and there's two reasons for that. The first reason is that in most markets, railways have a share of 5 to 10%. It's in capital cities, in large cities where rail has got a greater market share. In those cities, traffic will come back because cities rely on transport. And no matter what we say today, traffic will come back. I think the more important area is outside cities where currently the market share is extremely low. And if we do the job right, there's a huge potential market. And that's where, of course, engineers come in. If you make the railway easy to use, if you make the railway comfortable, if you make the journey on the railway useful rather than a chore, then I think the markets will grow. And of course, there will be a big influence on sustainability. If the railway can demonstrate that it's clean, that it's proper, then the railway will be able to gather more and more traffic. And so I'm very optimistic and positive.
Thank you very much, Felix. I've got the first question, which I'll read over to you. And if anybody else has any other questions for Felix, please complete the attendee questions section so I can feed them through to Felix. The first question we've got is from Anthony Jack, who is another colleague of yours, I guess. And the question is, you mentioned that Manchester and Australia were doing well, but what is going well in Australia, please?
It's basically the same situation. High traffic corridors with trains which are right at the limit of the technically attainable capacity, with lots of passengers who are not as disciplined as you would get on an underground system. And in both situations, COVID has shown where the weaknesses are of the day-to-day system. So if we can learn from the current situation and either reduce the number of trains and lengthen the trains, or learn how to educate our passengers, we can probably use some of the lessons. I hope that was a reasonable answer, Anson. I think the point of Ryan's and the point also of the people in the high reliability organizations field, they say you need to learn from the things which go well, because you can't predict everything. Yeah, sorry, Richard.
That's okay. Thank you, Felix. Anybody got any other questions? Because if there aren't any more questions, I'm just going to ask for the vote of thanks, and we can conclude things, and everybody can get on with their evening's entertainment. I feel a bit like an auctioneer saying going, going, gone. Okay, we don't seem to have any more questions. So on that situation, I'd like to hand over to Paul Birkett-Gray, who's the Vice Chair of the Railway Division Young Members, to propose the vote of thanks to Felix.
Hi there, good evening everybody. I'd like to say thank you very much to Felix for a really quite fascinating talk there. It was really interesting to start off with that sort of insight into how railways have been such complicated systems right from the very earliest days, with up to 150 operators in the United Kingdom, even in the 19th century, and how that's continued right up to the present day with Crossrails, multiple signalling systems, 29 different types of points, machines operating in Australia. And it was really intriguing to hear how you've applied systems thinking as a railway inspector in your analysis of the proposal for the violet signals for active gauge trains, and how, well, unfortunately, despite that perhaps not meeting your satisfaction for a perfectly safe system, was still eventually implemented, and highlighting the importance really of thorough safety analysis on the railways. And it was also really intriguing to hear about your sort of innovation in railway education with the development of the Railway Systems Engineering course, the MSc, and how you developed all these different ideas like the track building workshops at the Ecclesbourne Valley Railway and study tours to introduce the students on that course to the many different varieties of railway operation and technology in use around the world. And I was particularly keen to hear about your dedication to the Railway Children charity and fundraising for them, and look forward to hopefully supporting you when you're doing the sleep out in January of 2021. So I'd like to say thank you very much again for presenting today's lecture, and thank you as well to everyone who's attended today and listens to and watched the slides and taken part from wherever you may be around the world.
Thank you very much indeed.
Thank you very much.
And thank you also to Natalie for running the show, and for Richard for introducing me.
No problem, Felix. I think we'll close things now and let everybody get back to things. And thank you very much for coming along, and look forward to welcoming you at further Railway Division events, either virtual or hopefully in the future an actual meeting. So best wishes, all the best. Bye-bye.